Welcome back to the lectures on high performance scientific computing. The slides are again credited to Argonne Training Program on Exascale Computing from 2024 from the Argonne National Labs. In the last class, we had just started talking about reduction. Let us say that we have an operation where we want to compute the average of an array. Now, a serial code would look something like this, where you keep adding all the individual elements of the array A into a variable called AVE. We do this from loop index 0 to the maximum index, and then finally, to compute the average, we divide that variable AVE by the total number of elements which are there in that array A. So what we are essentially doing is that we are accumulating the value of all of these individual elements into one variable. Now, obviously there is some sort of loop dependence, because AVE can be computed only by subsequently adding each and every value of each index. Now, this sort of a problem is very common and it's called a reduction. And we can do this effectively parallelly, but we have to be a little careful on how we go ahead and do it. So there are parallel implementations for this in most programming environments, which allow you to do this effectively, hiding all the sort of gory details from the programmer. So typically the reduction clause looks like this. So you have a statement called reduction, and then you have what is the operation that you want to perform. The operation could be either getting a sum, getting a min, getting a max, so on and so forth, and then the variable list on which this operation needs to be performed. So what effectively happens inside the parallel work sharing construct? First, a local copy of each of those list variables will be created and initialized depending on the nature of the operation that we need to do. All the updates happen only at the local copy for each of those individual threads. Then finally, the local copies are reduced into a single value and combined into an original global value. A simple example would be if I wanted to create a sum of all the elements of an array. So if I look at the previous snippet of program, so this is how I would parallelize it. I would say hash pragma OMP parallel for, have a reduction statement, reduction clause. The operation that I'm doing is summation, and the variable that I'm working on is AVE. So the moment I put this directive, what essentially is going to happen is that the loop index from 0 to max is going to get divided appropriately based on the number of threads that are going to be created. Now, each of those threads is going to compute its own copy of the variable AVE, which is going to be a partial sum. So effectively what's going to happen is that the number of AVEs that are going to be initiated is going to be the total number of threads that are initiated. Each thread will copy its own, make its own local copy of AVE, and then implicitly a global AVE will be computed critically. All this operation is done hidden from the user. And then finally, we can safely compute the average by dividing the AVE once it is out of scope of the parallel for, which will now be the global AVE, by dividing it by the number of elements, which is max. There are many different reduction operations that can be done. We can do reduction operations on sum. We can do reduction operations on products. We can do reduction operations on negations or subtractions. We can do it on min. We can do it on max. And appropriately, we need to choose the correct initial value for the global variable. It is quite obvious if you are trying to do any sort of addition or subtraction, the initial value should be 0. If we are doing it for a multiplication, then the initial value should be 1. If we are trying to do a reduction operation, trying to figuring out either the minimum or the maximum, for minimum it should be the largest possible number, for maximum the least possible number or the most negative number. We can also do reductions on logical operations, and each of those logical operations have different operators based whether you are using C, C++ or Fortran, and will have different initial values based on C, C++ or Fortran, which are given over here. So these are the different reduction variables. We won't cover this all completely in this class, but it is left to the user to figure out how to use these logical operators. Now we can go back to the same exercise where we were trying to compute pi with a loop construct, and we want to now minimize the number of changes to the serial program. We started off with a serial program and we want to minimize the number of changes using the different constructs that we have learned so far. So we can initially create a team of parallel threads using the hash pragma OMP parallel function. Then we can create a local scalar x, which is going to hold the value for each interval. And then I can then say, let's do a hash pragma OMP for reduction in the variable sum. Now, sum is going to be computed parallelly for the threads. Now, the number of threads can be decided at runtime for this, and the for loop will be split up based on the number of threads. The loop index, we must remember, is local to each thread by default. If we do not do that, then it's going to be problematic. And then finally, you can compute the global value of pi. We can reduce this lines of code by simply putting a hash pragma OMP parallel for with the reduction clause saying that we are going to use an operator of plus over the variable sum. So you can now see that we took a serial code which was basically without these OpenMP directives, and we just added 2 lines of code and have now made it completely parallelized. This code right now is also agnostic to the initial number of threads. The number of threads can be set dynamically at runtime. If you run this code and if you look at it with this simple reduction clause, you can figure out that the timing is very similar to what is being done with the old critical loop. When you go to 4 threads, it takes a little bit more time compared to 1 and 2 threads because the reduction operation increases some amount of overheads in the background code that is being generated. So what we have traded for is the ease of programming for some cost in time. We can obviously go and be more explicit in programming using the critical statements and to get some more performance out of the code, but that's going to work only for very simple codes. If the codes are extremely complex, it is probably better to use these sort of reduction statements. The other thing we need to know is that all these critical statements and barrier statements are really expensive. The reason why they are expensive is because there is an implicit way in which only one thread is allowed to do things at one time. So because only when one thread is allowed to do something at a time, other threads will be just waiting. Barriers are very similar because threads will work at different speeds, and the thread which reaches the barrier first will then have to wait until the slowest thread completes all its tasks and reaches that point of code. Now, if you look at this particular snippet of program, here there are certain data dependencies. So because of certain data dependencies, it implicitly a barrier needs to be put after the statement AID is equal to big calculate one function of input of ID. But once that is done, you have it followed by a parallel for, where threads are doing some sort of calculations independently, and the next set of calculations might be completely independent of the previous set of calculations. Because an OMP for has an implicit barrier at the end of the work sharing construct, all threads would naturally come and wait until all of the work is finished. But because the subsequent for loop does not have any data dependency, this is a waste of time. So if you can put a no wait clause, then you can go ahead and have no implicit barrier. So for essentially what it means is that for the second for loop, each of the threads, once it finishes the for loop, it will go ahead and do the next programmatic statement without waiting for other threads to complete its relevant calculation. So essentially what we are trying to say is that the function big calculation 4 does not have any dependency on big calculation 2 if other threads have finished it or not. So you can safely go ahead and start the fourth calculation function even if some threads have not finished calculation 2. But that's not the same for calculation 1 and calculation 3 where there are implicit barriers. So what we are essentially saying is that there's a barrier here which all the threads will come and stop over here. There's a barrier at the end of this OMP for, all the threads will finish this OMP for and stop after calc 3. But after calc 2, the threads will not wait because there's no data dependency and go ahead and do calc 4. And then finally, obviously there's an implicit barrier at the end of the parallel region where all the threads will get stopped. But this is very critical in the sense that as a programmer, you need to understand where it is safe to skip and avoid synchronization and where it is unsafe. Because with great power comes great responsibility. You might end up with corrupting the data if you do not understand these things properly. The positive side of this is that you will be able to extract better performance if you put in these no wait clauses and use it safely. We also need to understand different things about the data environment that OpenMP uses. So the default storage attributes, how do variables get assigned? Are they thread safe? Are they shared between the threads? What is local? What is global? We need to understand it. Because this is shared memory programming, by default, most variables are shared. Global variables are shared amongst the threads. So in Fortran, if you use common blocks, if you use module variables, if you use save variables, these are shared among threads. In C, scope variables, static variables, everything is shared, both whether they are dynamically allocated memory or statically allocated memory. But not necessarily everything is shared. For example, stack variables in subprograms of Fortran or functions called from parallel regions are private. Automatic variables within the statement block are usually private. So if you give an example over here, so you have double A10, you have the main program, you have index, and then you have a parallel section. Here, the variables A, index, count, etc. are shared by all threads. But the variable temp is local to each thread because it's declared within the function work, right? So each thread will now initialize its own variable temp of length 10 and then go ahead with it. So we can change the storage attributes of these variables. We can say that certain variables are shared, certain variables are private, certain variables are what are called as first private, and we will understand what each of these clauses mean. They can be used for both parallel and for constructs, other than shared, which can be used only for the parallel construct. We can also force the programmer to explicitly define storage attributes, in the sense that if we say default none, which is usually a very good programming practice, that means the programmer explicitly has to declare which variables are shared and which variables are private. And you can do this only on parallel constructs. This is generally a very good programming practice so that you never make the mistake of using a shared variable as a private variable or vice versa. Let us look at this simple example where we have a nested loop. Now, one of the first things that usually catches OpenMP programmers is the fact that when we have nested loops, that the first private loop, or rather the loop which is parallelized first, the topmost loop, the index variable is private by default. But the second loop, which is nested within the first loop, the index is not private by default. And this can lead to a lot of confusion. Typically, if you are working with two-dimensional arrays as shown in this program, here, unless I specify that the index j is private in the parallel for construct, it is not assumed that j is private, and j would be then shared amongst different threads, causing abnormal behavior of the program. But if I indicate that j is private, then each of the threads will have its own copy of j, which then makes this program correct. When we use the private variable, it creates a new local copy for that variable. But the private copies are generally uninitialized, and the value of the original variable is typically unchanged after the region. So, for example, in this code, I do say that each thread has its own copy of temp. While I initialize the value of temp over here, it is being done only for the serial part of the code. It is not being done for the parallel part of the code where multiple threads are being generated. So, different threads do not have this initialized value of temp. So, when I do this sort of addition over here of temp, it is quite possible that I am going to get spurious answers, because we do not know what variable is being, what is the initialized value of temp over here, and temp is 0 possibly over here. We are just calling the initial variable, right? So, we have to initialize the shared variable correctly, and for that we use the clause first private. When we say first private, and in this case first private is assigned to this value increment incr, here each thread gets a copy of incr, which is then initialized to this value 0, which has been written upward. So, each thread now has a correct initialized value, and the computation can proceed correctly. So, for example, I can now say that we have different variables, some of them are private, some of them are first private. So, what does essentially happen over here? If I say there are three variables, a is equal to 1, b is equal to 1 and c is equal to 1, and I have this sort of a parallel declaration where I say b is private, c is first private, and I make no mention of a. That essentially means that a is shared by all threads and is equal to 1. b and c are private to each thread, but b's initial value in each of the threads is undefined. C is private to each thread, but its initial value is 1. After the parallel region, b and c will revert to its original value of 1. A is either 1 or whatever value is being set inside the parallel region. So B and C will retain its original value, will not get it modified by each of the threads, and will return to its original defined value before the parallel region. Now you can force the programmer to use default none, where now you have to explicitly specify which of these variables are shared and which of these variables are not. Now this is a very good programming practice, but it increases the workload, because if you fail to mention what these variables are, the compiler will complain and will not compile the code correctly. So you can put the default clause on the parallel workshare constructs. So for example, I can say hash pragma OMP parallel for default none, reduction on the summation operator, or rather the product operator on X. The compiler here would now complain about several variables like J and Y because they are not being shared. So you need to understand how these default variables work. If the original variable's value is unspecified and if it is referenced outside the construct, depending on the implementation may refer the original variable or a copy of it. And this is generally a very dangerous practice because we are not sure about how the program would behave on different machines. So for example, if you take this particular bit of code where I have some function and I say the variable temp is private and I am calling this function work, and I do not know what this variable is. What is this unspecified copy of temp? So temp will end up having an unspecified value, and when you printf it, we don't know what's going to come out. So this is sort of a dangerous use of private. Thank you. In the next class, we will discuss the memory model.